I've released homework 6, so take a look. Shouldn't be too tricky. Just doing some symbolic MIDI manipulation mostly. So we will be looking at this particular package, SubUSpy. So you can sort of like read different type of input. You can read like MIDI file, you can read music XML. But the idea is that you can get some sort of, piano roll representation to show it, but you can also synthesize it to listen to some of the stuff that you have. So this is basically reading like this for Ellie's MIDI file, and then in this once you load it as the MusePy music object, you can show piano roll, then you can get the piano representation. This is just trimmed to the first 13 or 12 quarter notes so that you can see it. Otherwise, it's too long. But also you can synthesize it. Just do m dot write audio. So m is once you read it. So it should be pretty straightforward. So once you load it into an object, you can print it, and you can see this is exactly what inside the model that's storing. So you can see there are like metadata in the first part. You have the resolution. This is sort of like the each quarter note, how many time steps you have. And then you have tempos events. So this is like in MIDI file, you have like at time 0, you set tempo to QPN 72. At another, timestamp, you set it to another value, but here is the same value anyway. You have key signature. So this is the way how MIDI represents stuff, and you have time signature. Cool. Anyway, and then you have a bunch of tracks. So each tracks is, a program, like the MIDI program, what instrument you're using, whether it is a drum, and a bunch of notes. So these notes would be the actual MIDI data that we usually talk about. But anyway, by using MuseFile, you can turn like a MIDI file into this thing, so that you can do something with it. So you can show the tempos. You can also change the tempos by just replacing these, or adding your tempo variation over time. You can also look at the first track. It's just what program, what instrument, and a bunch of notes. And for each note, it's just like, when does it start? What's the pitch? What's the duration? What's the velocity? This velocity is the MIDI velocity. Anyway, you can also trim it into 12 quarter notes. So the resolution is how many time steps you are using for each quarter note. So if you times it by 12, then you basically can turn it into 12 quarter notes. So this will be the output. If you trim it to 12 quarter notes, then you can also write the audio by just doing this function. So that's how you sort of like read a file. You can read MIDI file, you can read XML file. So the first question basically just asks you for doing that thing again, but this time do it with another file, use the XML file. So you would just synthesize it, and you can change the instrument by, manipulating the track, basically the program. So you want to get the first track, but you set the program to another instrument. And the other question will be, get the tempos, but changes to another value. That's basically what you want to do. But also using MuseSpy, you can also create MuseSpy music object from scratch. So this will be helpful if you are doing, say you're doing a symbolic music generation system. So you get a bunch of output like MIDI files. Then how do you turn that into MIDI file? You can always just write it into MIDI files, but it's not that simple. So you can also do it this way. Say you create a new music file, music object. You get a bunch of notes. That's, say your output of your music generation system. So in this case, if you look at this, it's just C, C, G, G, A, G. So this is just Twinkle Twinkle Little Star. And you have the time first note 24 because we are using 24 by default for the tempo resolution. So this is the first quarter note, second quarter note, third quarter note. So you basically get the Twinkle Twinkle Little Star. So you can build a track using these nodes. By default, you will use, first program 0, so grand piano, and then you append it to the music object. So now basically this music object has one single track that's, piano and contains a bunch of notes. So if you show the piano roll, you see this, C, C, G, G, A, G, basically. You can also just extend that track. So M20 will get you the first track, and then you can extend it with a bunch of more notes. So now you can extend it for the rest of the first melody. And finally, you can set the tempo. And once you set the tempo, you can write it. So you can just synthesize it. So it can become handy. You have a symbolic music generation system, add up a bunch of notes, or you're just having fun. You wanna write something. But anyway, this is it. So for the other question is that you just following the idea here, and then add another track, the chord track, to the melody. So basically create another track, a bunch of new notes, and if you want to do it simple, just use triad chords should be fine. But basically, you want to get another track that has the chords. Yeah, basically that's like that. This will be a chord, so all started at the same time. C, E, G basically, and they have the duration for more than a quarter note. This is 4 quarter notes. And then you just synthesize it. That's it. Cool. So that will be the first 2 questions, and the last question will be just playing with UCFX. Feel free to play with it, but I guess these are the questions. Just look at it, what kind of text prompt you can do well, and try to break it, I guess. This is always fun. So looking into MuseFX and see what kind of words that's just not usable, or it just doesn't doesn't succeed to capture those text prompt. So one thing MuseFX explicitly prohibit is sending composer name or artist name. So if you want to use MuseFX and then send in Taylor Swift, you cannot do it. That's explicitly prohibited by MuseFX, which is their way to avoid unintended copyright infringement, even though their own sort of training data, as far as I know, they have mostly stock music, so they are not trained on copyright music data. Cool. Anyway, that's it. Shouldn't be too tricky. You might spend some time working around with MusePy, but pretty much you've got everything. Just follow what we have here, and then the most tricky part would be creating the core track, but pretty much you just follow this, add another track to this object with all the notes. It might be a little bit tricky to think about how you get those notes, but shouldn't be too tricky at the same time. Questions? Yeah. Oh.
Can you say again what the pitch, like what the numbers correspond to?
Oh, so MIDI pitch. So basically all you need to know is 60 is middle C, and then everything else just semitones away.
Okay, semitone.
Yeah, so 60 and 72 will be C1, and then yeah, so if you count, this will be G, because C, anyway, 62 will be D, 64 will be E, and then 64 to 65 will be F, and then 67 will be D. So that's pretty much the MIDI pitch. Yeah.
constant instrument size?
Oh yeah. So here we don't set the program. But if you look at it, anyway, we could try it here. Basically you can just set it to program equal something else. 10. I don't know what 10 represent, but I think 48 is some string. And anyway, I mean, you can just set the program. If you look at this, if we don't provide the program by default, it will use the grand piano, the first program. That's the default of MIDI anyway. But yeah, one of the question, I guess, is just changing the program. Yeah, this one, I guess. Change the instrument to church organ, so MIDI program number 20. But one thing tricky is that in MusePy, we are using 0 bass because of Python. The MIDI program are defined using one bass indexing. So you will want to set the program number to 19. That's the tricky part. But anyway, you can set program equal 19, then you get the church organ sound. Yeah. Cool. So you just change it and then you write the audio again, then you get the another sound. Cool. Cool. Then that's homework 6. Shouldn't be too tricky. Yeah. Oh,
Sorry.
I just go with
How would we change, like it keeps on saying the default temporal resolution, the 24 time steps, like that kind of like implies that we would be asked to change it.
Oh,
Where,
so we are not changing the tempo resolution. We are changing the tempo. So tempo resolution is like the time step. So it's like, you have say, so it's like how many time steps do you have? So in this case, we have 24, so that you can, do maximum like something like this. I'm not sure if it's 16 notes or 13 second notes. I think it's 13 second notes. Anyway, this is the maximum you can represent within 24 time step. So you think about time step as the way how you do the piano roll. So this will be 1/4 note, but how many, slides you have per quarter note. So when you are doing tempo change, you are not changing the temporal resolution. You are changing the tempo. So that's a MIDI tempo. So basically how long this part corresponds to in second. So that will be the BPM. So that's like two different concepts. So one way people nowadays do MIDI file is that just set a high enough resolution, then you will be fine. Everything will be in that resolution, should be fine. But traditionally, MIDI file was built to use the minimum resolution as possible. But over the time, people just hack it in some sense. But that's like historical reason that we have that resolution thing. Yeah. So resolution 24, meaning that this first beat has 24 slices. So the internal piano roll will be, 24 ones here. So if you want to change the tempo, what you want to do is to look at this ends up tempo thing. So if you print the tempo, it will be this thing. So if you want to have a constant tempo, you want to change to 120, then you just set this tempo things. If you're loading something else, then you can just do something like this, musepy.tempo time equals 0, and then QPM equal 120. So this will just change the whole tempo. All the tempo, remove all of these, and then just replace it with just one single new tempo. So this is the case when you are loading an existing existing MIDI file, so you have to replace it. If you are just creating your new object from scratch, then you can pretty much, once you get all these, then you can just put it here that, set into the tempos to just one single tempo event. Then you get that QPM. Cool. So if you change the tempos, when you do show piano roll, you won't see any change because it's just how fast you play these notes. But it's basically still the beat. But when you write the audio, here basically, you can change this to 120 or 80 to change the tempo. But when you write it, you will see a different numbers. But it will sound faster or slower. Cool. Yeah, but that's it for homework 6. Have fun, I guess. Cool. So let's continue and try to finish what we talked about last week. So last week we were basically talking about, the current, how, sort of like MusicFX, Music Gen, and all the cool or sort of like state-of-the-art music generation system, how they work. But basically they all follow a similar idea, the way how we call it like latent diffusion or latent music model, latent music generation model, or even think about some of the image models like Adobe Firefly, Stable Diffusion, Midjourney. They sort of all use the same idea. Even Google's DALL-E, OpenAI's DALL-E, Google's Image Gen. There's so many, but anyway, most of them are using the same idea. So the pipeline is that you're training an autoencoder first. So you are not working in the raw waveform domain. Rather, you sort of like train some like MP3 like codec. So that you have a more compressed space, which we call the latent space. That's why the name latent generation model. And then you compute the latent vectors from a bunch of files that you have. That's your training data. Then basically you get a bunch of latent vector that represent the original file. And then you train a latent generated model. So this generated model is not generating these, song directly, like waveform directly. Rather, they are generating the latent vector that represent the audio. And finally, once you can have this, latent generated model, then, you generate a bunch of vectors, then you just decode them back to the waveform. So the idea is basically that, we don't want to generate stuff in the waveform domain. It just sounds too crazy. We've seen, WaveNet, but, it just seemingly, computationally too intense, but also it just not the easiest way or the most efficient way to do stuff. That's not fast enough. If you use some of the model that you see today, they are, reasonably fast, that you can get something even faster than real time. So the idea is that then we just train to generate stuff in that, sort of like MP3 or codec space rather than the waveform space. So that's basically the idea. But everything else is sort of the same, that, you're still using some of the all the generated model. You can use GN, you can use diffusion, you can use VAE, you can use all sort of like generated model. So this is something, irrelevant or sort of like orthogonal to the models they're using. Cool. So basically these are what you need to train. You train an autoencoder, but also a latent generated model. But when you get it, this is what you are doing when you're calling the MusicFX, that, there will be some random distribution. You will get a random number or random vector, and then turn it into some latent vectors, and that latent vector will be decoded back to the song that you hear. Cool. So last week we talked about audio gen. This is the most brutal force one that, you just turn, a waveform into a bunch of tokens. So you can think about these tokens are just like, say MP3 bytes, or, think about it like an alien language. Then what you want to do is to go from English to some, MP3 language or alien language that correspond to the actual sounds that you hear. So, this is basically, you can think about it like a translation model. So machine translation to, from English to a language that you don't know, say alien language. So basically you want to train a machine translation model. So that's pretty much what AudioGen do. So this is what Transformer was proposed for. So they basically just grab the Transformer model. So this is inherently, not inherently, this is basically a transformer model that just translate this, input into some audio token. And so they can do a bunch of, generation. So this is in audio domain. So you have like sound effects, whistling, dog barking, people shouting. But they also train the version for music gen we've seen last week. So they are using more, licensed music, but also stock music. So this is music LM. This is the one that we will be looking into in homework 6. So it's much more, not much more, I guess, slightly more elegant than AudioGen and MusicGen, in the way that it has, multiple layer of abstraction of music. But pretty much what we get from this is that, this model run much faster, but also it has better understanding of text versus text and music, the alignment between them. So this is because we have this text to music correspondence model, which is called Mulan. Anyway, and if you look at their data set, it sounds crazy. So this Mulan model itself is trained on 44 million 30-second clips, which total in 370K hours. So that's how you train this model. And we've looked at it last week. So this is like clip. They basically train the music version of this thing. So the idea is that you have two encoders. You want them to, map to the same space or share the same space. So in the end, you will get something like, these things. So the cat image and the cat text go through these encoders will be stamped to the same spot in your latent space. So that's what you need to get from this clear model. So you want to map closer these things and make everything else further away. So that's the contrastive learning part. But, once you get this, you can think about it like, when you're training this Mulan model, what you get is, take a rock music, and then the caption will be, a soft rock music with, I don't know, like cheerful vibe or whatever. Then you can sort of like understand how, text and music correspond to one another. And you will have, say like a jazz music, blah, blah, blah. And then you have the jazz song. So, the idea is to learn how text and music correspond to one another. And that was sort of like be the interface, how you interact with these models. Cool. So this is how they train it. But the idea is that we go from the Mulan thing. So we take some audio and we extract the Mulan representation. So this representation will be, very high level, say, a song, a rock song with, slower tempo that has a soft timber-ish thing, very high level idea, talk about genre, talk about the general vibe, talk about the general timber rather than all the details. And it will first generate some of the details, and then the second stage generate all the details. So you can think about this as like very high level description of the music, and this will be, middle level description of the music, and this is like the exact bytes or exact, MP3 or exact waveform that you want to generate. But anyway, the idea of Mulan, the reason why it is clever is that, during training, we are not using actual, text to music data, but rather we just need to get a bunch of music without the text. So we get a bunch of music, we use Mulan to sort of like get the like a pseudo thing to train with. And during inference, now we use text instead to send into the Mulan. So this Mulan model, as we said, is maps the text and music to the same space. So that's the clever thing about them. So, during training, you are using audio to train this model, but during inference, when you are, sending out, when you play with music FX, you are sending, text rather than the audio. But this text can be turned into the same Mulan embedding so that you can use it to get everything out. So basically, that's the core idea. You train with audio, but you extract that Mulan embedding so that you learn to reconstruct the original music. But at the inference time, you send text instead. But because of Mulan, you can do it the way you want it to be. Cool. So with all these details, anyway, this is the interface that you have with MusicFM. So now it's released as MusicFX, where you can play with it. This seems to be overly detailed than what we typically send it. But basically, it can generate something. Anyway, another version. Voice? No. I don't think so. We could try. I don't think so. So all these models tend to not doing vocal because it's too tricky for them you basically will fall into very tricky situation. So none of these models usually they don't do vocal. If you want to do vocal, usually you do it with voice cloning. So you sing and then you turn it into something else and put on top of these things. Yeah, usually they're gonna do vocal. We could try. I think it will fail elegantly. I don't think you can. Maybe you could. Who knows? Yeah, so vocal at all. It does sound like it's waiting vocal. Yeah. Cool. So yeah, it doesn't do vocal because of the copyright issue mostly. And also that, with the model here, it doesn't actually do vocal as good as it is. So if you look at Suno, I think, most model doesn't do it. Suno is only sort of like the few models that actually do vocal to generate it. Most company are not doing it because it's too tricky to handle the copyright thing, and Suno likely just doesn't care. And so how they do it is that, you generate the lyrics and then you use, singing voice synthesizer to turn those lyrics into the music. So in that sense, you could generate the background, all the other, part of the music, and then you generate melody that align with the music, and then you synthesize it using singing voice synthesizer. So that's how Suno do it. But most of the other model are like, well, we won't do vocal at all. But there are also some, vocal studio as you see in Moises, but it just totally sort of like two different fields. and Suno is sort of the only company. There are some other, but few companies doing that both. Cool. So this is Music FX. So homework 6, just try to break it. So, you find something that it doesn't work, vocal. But also if you send in certain artist name, it doesn't work, but it could be more interesting. Look at, combination of doesn't make sense combination. Sometimes it does a good enough job, but sometimes you just totally break it. But that's the idea. So last week we also talked about, a little bit about this Music FX DJ. So this is sort of like different from this. So this, just generates 30 seconds, or you can set different length. So you can also do maximum 70 seconds. So seed is the, random-ish thing. So, these two songs will have different seed. But Music FX DJ is another thing that, it just generates sort of like a never-ending streaming audio radio for you. So, it will just look at this. It will just keep generating like 5 to 10 second chunks over time. So you can sort of like hide stuff. No, that's pretty bad. Yeah. Okay, cool. And you can sort of like change their. You can sort of like slowly more from alternative country to chiptune. But anyway, this is another sort of like interface that's like looking into, it's like continuously never-ending radio that, you can sort of like add different stuff on the water DJ. I don't know what it means. Anyway, typically, if you want to get a more smoother transition, then you have to do these things, smoothly. And you also imagine like in Max MSV or, whatever slider, you can slowly do it rather than, on the computer, on laptop, it's kind of tricky. Or you can play on your phone. But anyway, this is just another interface for playing with Music FX. But I guess more interesting is Jepco Collier do this. So this is like a 2-hour session.
Good morning.
But basically,
good afternoon. I'll talk you through the controls.
Playing with Music
and
FX.
also, it's worth saying before we get started that if you want to, first, and we have liftoff. Suddenly we're in a cool. I like it. That's fun. Experiment a little bit more and see. Oh, let's get rid of this. What I wonder best. I'll show you what a charango is because I know you're wondering. A charango. This is what it sounds like. Whoa! I mean, come on.
Anyway, it's like 2 hours, and you just keep talking with the it's online. There's online chat, so people just sending cool prompts for him to try. But anyway, this is what he ended up with. He also sing and add some composition into it.
Some small tweaks as we go, but
the end result, which is pretty cool.
All right, look, thanks everyone. This has been great fun.
Almost 2 hours.
Thanks for stopping by. I could obviously go forever. It almost doesn't need to be said, but I don't have forever because I have to go on tour in a few days, so I'll have to go on tour. But for now, this is what we've created as a team, I must say, with all of your incredible suggestions, with the help of Music FX DJ, which you see here before you. Yeah, this is the creation of the day. Here we go. 5, 4, 3, 2, 1.
I don't know why my laptop is doing it.
Yeah. Uh-huh. Oh, there you
Cool.
go.
So that's what it is. I think it's pretty cool. As an initial attempt, you can sort of see, if you watch it, part of it at least, you can see how it just exploring interesting sounds with Music FX DJ, and almost always the time that it's not just doing simple things that just create a rock song or create a cliche pop song, but rather I think Music FX DJ is interesting in this particular piece is that when it morph from one genre to the other, so you can hear that in this song particularly whenever there's section changing, that's when the interesting stuff happened. So I don't know, we'll see in the future. Maybe people will be looking into some of these transition that sort of like has its own vibe rather than other things. Yeah, and there's a lot of stuff he added rather than just relying on the AI whatever material it generated, but it's sort of like exploring that interaction with this model. Cool. Anyway, it's pretty cool. So take a look. It's like 2 hours, but it's kind of interesting to see how he interacts with the model, and in a way that if you just go on the website, it's like, well, this is what we can do, but look at others how they actually do it, so that you can get inspiration, but at the same time get something out from the model that for most people, it's like, very cliche stuff, but still you can build something interesting on top of it. Anyway, so that's pretty much it for the whole, music generation part. There's something else in the end, but this is sort of like things you've seen so far for the past 2 to 3 years, I guess, that people are hyping with music generation. But under the hood, what you are doing is this latent model that basically just sort of like not generating the waveform or spectrogram directly, but rather generating the latent stuff. All these things are sort of the industry version of it. So in academia, we also have a version Music LM. Everything is open source, but you can basically more easily to hack it. And it's trained on audio stock. So another stock music data set. Anyway, I will show you this. This was the same idea, text to music generation, but this is one of the cool example that you turn a poetry into song. Cool. So that's what it is. It's always funny to see at the end, it just and with that, I don't know, anime vibe. I don't know why. Yeah, but this is one of the things you can do with these models, and you can imagine, interesting, I don't know, interaction, or I don't know, audiobook, or think about like an exhibition, and you will have some text, but you sort of like augment that experience with some generation model. But this is open source version of all the audio gen, music gen, and music FX. It does sound pretty stock music like, because you see whenever he's mentioned that slow, it just sort of becomes that game music ish. But also it has a certain vibe that's sort of like more functional than the music that we listen to mostly. So these will be think about stock music. When they are using it, is mostly for YouTuber, or for content creators, or for gaming company. They want to find those royalty free stock music, so that they can put it in their their games, or even some compositions, but mostly those are more functional than the music we have mostly. Cool. Anyway, that's musical LEM. So again, the idea is train an autoencoder, compute all the latent vectors, and you train that latent generated model, just generate those latent vectors. Once you have the latent vectors, you can turn it back to the audio. And so that's what you see during the generation result. But these are, the models that we have, or, commercial models, but there are also some interesting creative application of these models. So this is another interesting model.
This is Unloop. Unloop is a looper that wanders around your original musical idea by generating variations of it. Unloop is powered by a generative model called VampNet, which generates variations on audio using the original loop as the prompt.
Cool. So you get the idea. This is a looper that doesn't repeat itself. So you send in some, audio as the original loop, and then over the time you just code this, music generation model that just do variation of it. So you create this kind of like interesting looper that you can sort of like control how far away it could go around with the original idea, but it sort of stay constrained within range with the original loop that you send in. So you can play with it at this link, but also this is the way how they train this model. But basically they are not training, music generation model from scratch. It's not like text to text, text to music generation, but it's more like, well, you have this original audio. Can we sort of like get rid of part of it and then resynthesize the masked out part. So the idea is that so you get some audio and you mask out part of it and you want to resynthesize those maxed out part. So basically just train a model, some details. But basically what you want to do, the tokenizer, you can think about it like the codec that we were talking about. So you will change this audio into a bunch of, say, MP3 codes. And what you want to get for the output is a bunch of codes that correspond to that. So now you are not training, text to code generation, but rather you are doing this, certain part are blackout and you want to resynthesize those. So this is like neural codec. What you want to do, what they call this VampNet, it's sort of like something like CocoNet we talk about, like the Baccarat thing. So part of it it's missing, and we want to see what are those. So you sample it first, and some of them will be high confidence, some of them will be low confidence. Keep the high confidence one, redo the low confidence ones. And then do it again. Once you have the chorus, so the chorus will be the lower part. These will be, say baseline chords, each thing, and then it will get all the fine grain stuff later. But anyway, this is how they do it. So when initially you get, these things, everything else is maxed out. So in t=1, you sample it, and some of it will be more confident than the others. So you keep them. And in the second iteration, you generate all of these stuff, but some of them will have more higher confidence, then you keep those. So you go on and go on until you get everything out over the time. So that's the idea. So sample a subset of the most confident predicted code tokens in each iteration. And they can do a bunch of cool things. We can just look at the what's going on. Okay. So this periodic thing is that you grab an audio and you mask out part of it and then you regenerate it. Beat driven is that you use a beat tracker to get rid of part of it, correspond to beat, and then you regenerate it. And impending is that you just completely get rid of the middle part and then resynthesize the music. So we can listen to the.
Hi, my name is Hugo Flores Garcia, and I'm here to present method is known to. There are some aggressive models can tokens in a bidirect known as. For example, we can prompt VampNet by taking some input music, unmasking every 13th time step,
So this is
and then
the Pascal stuff. So you only keep 1 out of 13. So this is what you get.
and then generating the rest.
It's just a,
Alternatively, we can use a beat tracker to
echo,
locate
in some
all the
sense.
beats in a song and only unmask the tokens at the beat.
So these are what you keep.
And then have VampNet generate the rest.
Sorry about it. Let's do it again.
Or we can interleave tokens from 2 different songs. And have VampNet generate a mashup of the 2 songs. VampNet can be used as an
And this is
interactive.
what we saw, the on-loop thing. But basically, VampNet is like audio to audio, which is interesting because you can create a bunch of interesting, ways of interacting with these model. So, this is one of the a nice example that, text to music generation system seems to be, whenever people are talking about AI music, but especially for generation. But there's a bunch of more interesting models that you can use rather than, just sort of like constrained with that text. And, text is not always the perfect way to do music. But some of it, look at Jacob Collier, you can still get something out from it, but that, there's a bunch more. Questions on this? Cool. So, the idea is that, well, sort of like the Baccarat thing we saw, you turn them into some, codec, and then you max out part of it and you resynthesize it. And the interesting part of this is that how you redo this in a meaningful way. So you can do it, on the beat, periodically. You can also do impending, but also, the on loop thing is that, you just put it into it and then get rid of part of it and then do a slight variation of the input song. Cool. But also there are some more models that could control these music generation systems. So ControlNet is one of the things that you might heard in some case that, you can control the image generation model. So if you play with some of the Stable Diffusion and Midjourney, you will see some capability of these. You can go from sketch to the some image. So if you do nothing, you get these, but you can sort of like prompt it also with your text. But you can sort of like control the pose of it. So the idea is that can we add controls to a trend text to image diffusion model? So basically this is ControlNet. I won't go into details. But the idea is that you get a set of control, the exact same copy of the diffusion model, but that it will learn to understand what your condition is. And this is how did we look at this? Yeah, I think so. But anyway. So the way how they do this visual is basically using control F. So that is stay at the same place. You know, it won't just move around. And you can also do some dance. So these are all possible because of control F.
My circuits process, data they churn for the warmth of truth.
But anyway, you know, this is like a year ago, and at that time, only visual can do it. But now you can also do some simple control music. We'll see much better stuff in the future. But for now, what you can do with music control NAT is that you can at least control like melody, dynamics, and rhythm using pretty much the same idea. So you have this text to music generation model. You've trained it in some case, but now you want to add controls on melody, dynamics, and rhythm to it. So this is what they can do, at least, the melody, it will match. So this will be the input condition you send to the model. And what you get is this. And then if you extract their output, you will see that they sort of like match in some sense. So we can look at some of the examples here.
Beat and tempo like this. Beyond melody, we can generate music with beat, down, phrase, and our method will adhere to the partial melody input and then improvise the rest like this. Beyond melody, we can generate music with beat, downbeat, and tempo like this. We can also use dynamics control to guide the overall intensity or arousal of a song like this. Finally, we can combine one or more controls together like this. We enable control by revamping recent.
Cool. Anyway, you can imagine this is from Adobe. So they are mostly thinking about, in video editing scenario, or, you're creating a soundtrack for your video. Then, you definitely wanted to align with the, visual tempo or the beat, or maybe someone's dancing, then you wanna, or someone's walking, then you wanna have that tempo. And, potentially you wanna create a certain scenario or transition, then you will want those controls. But this is some of the very early result how you can control stuff. But also there's another model, Vito, which is another model which is also kind of tricky to look at it. So the idea of this model is not to sort of like learn how to look at the text, the control that you have, but rather is that when we are doing diffusion model, is that we have the input, the text, upbeat, jazz music, and we would generate something out. But we also have that latent code, which is the random vector we send into it. So the idea of Vito is that, well, if we have certain targets feature, and we want to see, when we just send it into some random stuff, we will get something that doesn't correspond to the target feature that we are interested in. But can we sort of like do some optimization so that we gradually change this input condition, this input vector, so that the output will have a better alignment to the controls that we have. So, this whole figure is just doing that. But you can think about it like a Dito. I guess that's why they have the name. So, originally you have these things, and this Dito thing is that, in this space, you can sort of like morph around. And some of it would be, pretty away from the actual control. But, over time, you optimize it so that you change this vectors, move around this latent space, and see whichever direction will lead you to a better stuff. So, if you want to become a Pikachu in this shape, then, you just starting to move around in this space, then this, Dito will just reshape. And at the end, what you want to do is so that this Dito just reshape into a Pikachu. So that's still the idea. So, it doesn't, generate something that just exactly as the input, because sometimes it's impossible to find an exact match in the space, but at least you can get something close enough. So you can do intensity control. It could be helpful. I mean, I don't know, like car advertisement commercials. Structure condition. So this is the SSM, self similarity metric we've seen. So you can also use these as control. So if you control on this, you get that ABA structure, and you can see that in the output. Anyway, that's music control now and Ditto, but both of them are sort of like thinking about how you can control these music generation models in very simple way. And in the future, we will see interesting stuff coming up. So control that, you can control it with pose, you can control with different things. But you can also think about it if you turn that control into, say, I don't know, EEG signal or body movement, or more interesting inputs, then it will become more interesting over time. But also there will be ambiguity between how you map these different data to the actual features that you have in your music. Cool. We've finally done with all the music generation things. Any questions on all of these? Oh, good. We are kind of late. But anyway, we got 10 minutes. We can look into some of the search and recommendation thing. And on Wednesday, we will finish with editing. And yeah, and sort of logistically, next week, we will basically having, project consultation. So just book a time so that we can talk. Hopefully it will be 30 minutes. So, we'll be in this time, but we can also find another time if that works better. I will send an email, but basically book a time to chat on the project. Cool. I guess we can look into some of these. Cool. So the last part of the course would be talking about, more high-level thing. First, we will talk about search and recommendation, and the last module will be on music editing. So, AI mixing or, reverb-ish thing. So, just quickly go over these. So one thing that, still AI, but not generative-ish is not even AI, but I guess one thing important, music fingerprinting. So this is the thing that, in Shazam and Siri, that you have this ability to say, what song is playing right now. So these are all powered by, AI, but these are sort of like even long before all these recent deep learning thing, because they are based on a much easier algorithm. And also you have SoundHound, you can sort of like set what song we are listening to. So these auto printing, fingerprinting model, what I want to do is that you have a waveform, you want to sort of like get this fingerprinting model so that you get a fingerprint of this song. So what's the point of doing this? So mostly the most common use case is in audio identification. So think about, on YouTube, you upload some audio, you upload some video, and you will sometimes get some, copyright claim that you are using someone else's work. So how they do it? So the idea is that, these fingerprinting models should be trained or, clever enough or designed properly so that, for all the songs that you input, it will generate a bunch of, different fingerprints for these different songs. And once you have a new song, you just go through the fingerprinting model again, and you will get some, fingerprints so that you can match from the database that you have. So this is the basic idea of audio fingerprinting and how it's being used in, different systems. And, for Shazam, it's like, well, you have the song and then you see what the, fingerprint of that is, and then you do the match. For YouTube, the content ID we'll see later is that, looking into all the, content or, copyright holders, copyright work, and see whether your new video, your new upload content has part of it in the database. So in terms of, how technically that's being done, it's pretty much, things that you might know a little bit. Pre-processing, you just do a bunch of stuff, sampling rate, band filtering, and then framing and overlap. That's the STFD thing we talk about. Frame size, overlap, window size, transform. You can do a bunch of different stuff, but think about it like STFD, male spectrogram, stuff like that. And then you can extract certain feature. Some of it are implemented in Liberosa, but these are very simple algorithm. And then you do stuff. But basically, fingerprint modeling is just to compress the input audio into very compact thing that you compare with. So, ignoring all the details, what you want to do is, get the audio, and then you get some audio fingerprint that's sort of like you can use it to compare with different models. So this is one of the iconic fingerprinting model. If you look at their model diagram, it's pretty simple. It's just framing and Fourier transform. So this is basically STFD, and then ABS, you get the power, and then you do each different band. And for each different band, you just compute the energy. And the clever part is how you turn that into the beat. But anyway, that's basically, band-wise energy computation, and then turned it into some stuff. So, these example fingerprint blocks for the song is something like this. And if you turn this song encoded with MP3 and then turn it back to waveform, and then you do it again with this algorithm, what you get is this. So, seemingly the same. So they're just little, tiny error between them, but, pretty much you can get a really good idea of whether there's a match. So this is being used in YouTube Content ID, basically.
At YouTube, our goal is to give everyone a voice and show them the world. Part of building a platform that works for everyone is making sure we have sophisticated content management tools that...
Oops. Too bad.
At YouTube, our goal is to give everyone a voice and show them the world. Part of building a platform that works for everyone is making sure we have sophisticated content management tools that help content owners manage and protect their works. That's where Content ID comes in. Nearly all content claims on YouTube take place through Content ID. So, what is it? Content ID is YouTube's unique software system that was built to help content owners find
So this Content ID not only work on audio, but also on video. So if you send, say, I don't know, like Olaf to YouTube, they will still recognize it as, Disney copyright.
copies of their work on YouTube.
So it's
Content
like
ID also gives them options beyond taking
visual,
down
but
copies,
also the
which in turn allows YouTube creators around the world to share creative ideas through fan videos that may include others' original content. Here's how Content ID works. First, content owners give us audio or visual reference files that identify their works. Our Content ID database creates what is known as a fingerprint from these files. We keep these fingerprints in a database of hundreds of years of audio and visual content. Content ID scans videos on YouTube against these fingerprints to see if there's a match. Thanks to these fingerprints, Content ID can recognize audio, video, and even melodies when they've been covered or imitated. When the system finds a match between the audio or visual reference files and a video on YouTube, the content owner has three options. They can block the video that matched their content, they can monetize the video, or they can track viewer data to get detailed analytics, such as countries where their content is popular.
So yeah, that's pretty much just YouTube Content ID, but you see that three option. That's where things get interesting, is like, whenever you detect that content of your own, rather than blocking it, that's, maybe Disney like to do. But if you are a content creator, sometimes you want people to remix or share it into reels, then you want to get cash out from that. So, YouTube's content ID also help to, sort of like create that business model so that when people reshare, when people reuse your work, or, derive something from your work, you can get, remuneration back from it. Cool. Anyway, there's also tiny variant of that, is that cover song identification. So, if you look at this content ID thing, you will definitely realize that, well, it's nice to do, exact copy to detect whether there is a exact copy. So these things are sometimes used in, copyright detection, but also, there are also some debate on sometimes it's being too strict in some sense, that sometimes I upload something to YouTube and it will have a copyright notice that doesn't make any sense. Sometimes it has errors, but that's what it is for now. But cover song identification is a little bit different from fingerprinting, in that cover song is that it's still the same melody or the same thing, but just a different version of it. So content ID also work on melody, but also people are looking into how you can do better cover song identification. So the idea would be do singing voice recognition, then you get the transcript, then you can just do lyric match rather than doing it on audio. That sometimes could be tricky because if like two different singers sing the same song, if you compare the spectrogram, it doesn't match. But if you do singing voice recognition and extract all the lyrics, then you can do lyric to lyric match. But at the same time, you also have the tonal based matching system. But anyway, for cover song identification, you wanna grab more information than just comparing the waveform or the spectrogram together. So that's the idea. So you can extend that idea of fingerprinting to also detect cover song. Cool. We will talk about these next week, but this is audio watermarking. Anyway, the idea is to watermark your audio so that you can detect it. Some of the most iconic use case in MusicFX, if you click on the I thing about MusicFX, if you go to MusicFX website and then you click on at the right top, you see the I thing. It actually says something like use Google Demise novel watermarking technology Sync ID to embed a digital watermark in the outputs. So the idea is that they will embed a watermark in your audio that you could then tell. But whenever you release it, people knows that it's AI generated. So that's sort of the thing that people wanted to do nowadays. This will be the original file. And this is the watermark version. So, pretty much you couldn't tell, but the model knows that now this is watermarked. So you can use it to detect, you can sort of like, if you're a company, then you can sort of like watermark something with your own mark. For AI generated things, it's useful because sometimes you want to prevent, negative use case, harmful use case, then you want to watermark it. But also, if you are an artist or you're sharing confidential thing, then you also want to watermark it so that you have the whether it has been altered. Cool. We'll look into these on Wednesday, but also editing and mixing, which is cool. Cool.